Hello everyone, I am Amulya, Assistant Professor in Department of Electrical and Electronics Engineering, Savidya Institute of Technology. In today's session, I am solving the seventh problem in Module 2. So this is a quite different one and it is very important also. Most of the time this question has appeared in the exam. So I have taken the same problem which was appeared in the exam only. So now look at the given problem. So we have one generator is there which is having the rating 25 13.8 kilovolt and the subtransient reactance so XD double dash is 15%. It is connected to a transformer and this transformer will going to supply to the four identical motors. Here you can see there are four motors and all having same rating of 5 MVA 6.9 kilovolt XT double dash, that is subtransient reactance is 20% and the transient reactance is 30%. So here they have given the rating of the transformer. Only one transformer is there, 13.8 kilovolt slash 6.9 kilovolt, and the bus voltage at the motor side is 6.9 kilovolt. So this value is nothing but this is the rating of the pre-fault voltage. So 6.9 is the pre-fault voltage here. So here a three-phase fault occurs at a point P. So this is the point P. Here the three-phase fault has occurred. So now what you have to do, you need to find out the fault current at the fault point. So at this particular point, the fault current need to be calculated. So that is the first thing, and after that you need to find out the subtransient fault in breaker A. So here we have the circuit breaker A, that is this point, this is the breaker A. Here you need to find out the fault current. So what is the meaning of the breaker A means? You remember this is all the symbol for representing the circuit breaker. So here this is, there will be a circuit breakers are connected. So when the breaker A is operated, breaker A is operated is nothing but this breaker is once operated, it will be get disconnected from the system. So such a case, what will happens? How does the behavior of the system and what will be the fault current? That is what we have to calculate. And similarly we need to calculate the third one, momentary current IMM at fault at the circuit breaker B. So this is what the given data in the problem. So here you need to consider a base value of 25 and 13.8 kilovolt in the generator 1 circuit. So this is the given problem. So now we'll proceed with the step 1, calculation and drawing of the per unit reactance diagram by taking the base of 25 MVA and 13.8 kilovolt. So you can observe here MVA base new will be 25 and kilovolt base new of the generator is 13.8. So now by taking this as a reference value, I have calculated the motor and also the transmission line. I have considered this as a transmission line connected to the motor. So here only one transformer is given. So we'll use a HT section because this using this as a reference, that is a generator value as a reference, we need to find out the motor value. That is the motor base voltage. So here I have written 13.8 kilovolt multiplied by the low voltage value 6.9 divided by 13.8. So HT section formula only, LT section formula only have used kilovolt base on LT multiplied by the value of the LT value divided by HT voltage rating 6.9 kilovolt it is. So next what we have to do, we need to go with the reactance calculation of a generator, transformer and the motors. Since all the three motors having the same ratings, so one calculation is sufficient. So calculate the reactance of the generator, we have got 0.15 J per unit. Similarly I do it for the transformer and also for the motor. So this is the reactance for the transformer. Next, coming to the motor calculation, the reactance. Look at the given data here. So the two reactances are given, XT double dash, nothing but subtransient reactance is 20% and transient reactance will be 30%. But in the problem, everywhere they told you to find the subtransient values. So it is better to take the subtransient value, that is a 20% instead of taking 30%. So here I have done the calculation of reactance only for the subtransient value of 20%, that is J0.2 per unit. So this is the answer, that is J1 per unit. So next we have to draw the per unit reactance diagram for this given single line diagram. So here is the reactance diagram, and don't forget to mention the point where the three-phase fault has occurred. It is near to the generator side. So this completes with the step 1. So next we are going to proceed with the step 2, that is identifying whether the given system is loaded or unloaded, and after that we need to calculate the pre-fault voltage. So now observe the given data here. So nowhere else they have mentioned the ratings of the load, nothing but the motor. But one thing you need to observe here, they have given the bus voltage at the motor, nothing but 6.9. So what is this 6.9 indicates means it is the pre-fault actual value. So VPF actual will be equal to 6.9 kilovolt. But you have to observe that the fault has occurred on the generator side. So now what we have to do means we need to write the or we need to make sure that the generator terminal will be equal to motor terminal, so that we can consider VGT will be equal to VPF per unit. So for that calculation, so now consider the same reactance diagram only. So this is the generator terminal voltage VGT, and this is the motor terminal side, it is VMT. So here the fault has occurred at this point, so it is clearly understood that VGT will be equal to VPF per unit. But there is a twist in the given problem. They have given the VPF or the motor terminal value actual, that is 6.9 kilovolt is given in the problem. So now what we have to do means, so we need to consider VGT per unit will be equal to VMT. So how we got this means, if consider a current IL is going in the circuit, so now what will happens, VGT will be equal to, so we will get the current VMT, then the current IL will be equal to the reactance, that is J0.1. Since you know that it is unloaded system, because the power and power factor value it is not given, so this IL value it is all will be equal to 0. So now finally what we will get, VGT will be equal to VMT, that is the terminal voltage of the generator will be equal to terminal voltage of the motor. So based on this we'll proceed with the VMT calculation first. So this value will be equal to VGT value. So VMT actual divided by the motor terminal value base. So VMT actual it is given in the problem. So look at once again in the given problem, it is 6.9 kilovolt. So this is your actual value 6.9 divided by VMT base, that is a base voltage on the motor side. So that value also will be equal to 6.9 kilovolt it is. So we will get the answer as 1 per unit. So now what we can write, since VMT is equal to VGT, so this VGT is nothing but the pre-fault voltage VPF. So we can write VGT per unit is also equal to VMT per unit. This is also equal to VPF per unit. So the answer will be 1 per unit it is. So this complete with the step 2 calculation. So important thing here you need to remember is, so here even though the fault has occurred on the generator side, but in the problem they have given the actual value of the motor, that is 6.9 kilovolt. So now what we have to do means we need to consider the generator terminal will be equal to motor terminal, and by considering VMT is equal to VM actual divided by base, so we'll get the answer as 1. So this 1 will also be equal to generator terminal, nothing but the pre-fault voltage. So next proceeding with the step 3 calculation, that is the fault current calculation. So the formula is IF double dash per unit is equal to VTH by ZTH. So VTH is nothing but VPF only in the previous step, that is equal to 1. So next we need to find out ZTH value by rewriting the same reactance diagram by neglecting all the source voltages. So for finding the ZTH, the same reactance we have written like this way, and here is the point where the fault has occurred. So here you need to observe that all the 4 motors are identical and it is connected in parallel. So we need to use the equivalent reactance for all these motors, and then we need to add this equivalent reactance with the J0.1 reactance of the transformer. Then the sum of these two will be in parallel with the reactance of J0.15. So the same thing I am going to write here. So remember, we are using the formula of equivalent reactance. So that is 1 by x equivalent will be equal to 1 divided by x1 plus x2 plus x3 and so on. So this is how we are going to calculate the equivalent reactance. So the same thing I am going to do it here also. So Z Thevenin will be equal to, we have 4 reactances are there, all are connected in parallel. 4 multiplied by the reactance 1J, and that is connected in series with the transformer reactance 1 divided by J0.1, and this entire reactances, it is connected in parallel with the reactance of 1J0.15, that is the generator reactance. So after doing the calculation, so I'll write the final answer. ZTH will be equal to J0.105 per unit. So this is the reactance for the Thevenin's impedance. So now substitute this answer in the fault current formula. IF double dash per unit will be equal to, VTH is nothing but 1. So substitute this 0.105. So we will get the answer as minus J9.52 per unit. So next what we have to do means, we need to find out the answer, the obtained answer in terms of actual. So now look at the given problem. So the first thing they ask you to determine is subtransient fault in the fault point. So the fault point is near to the generator. Here we have calculated the fault current value, but in terms of per unit, this is to be converted into actual value. So next is the subtransient fault current at the fault point. So the formula is IF double dash actual will be equal to IF double dash per unit multiplied by I base. So IF dash per unit is minus J9.52 multiplied by I base is P base divided by root 3 into V base. So V base is nothing but where the fault has occurred, that is near to the generator side. So this base voltage 13.8 kilovolt we need to consider. So base voltage of generator. So P base is nothing but 25 MVA. Then root 3 V base is 13.8 into 10 power 3. So after the substitution, we will get the answer for the first question is minus J 9413.2 amperes. So this is the answer for the first question, that is subtransient fault current at the fault point. So next similarly we need to proceed with the second calculation, that is subtransient fault in breaker A. So that is at this breaker. So I told you already, so whenever the circuit breaker is operated means it will going to disconnect from the entire system. So because circuit breaker, it is nothing but it will going to break its contact when it is operated. So now in the second case what they have given, so here the subtransient fault will occur, that is at breaker A. So at that condition you need to find out the fault, that is IF double dash. So now what we have to do, the same reactance diagram we need to write, but here we have to neglect the circuit breaker connected to the fourth motor, because I told you once the circuit breaker is operated means this will be entirely disconnected from the whole power system. So now based on this I am going to rewrite the same reactance diagram. This reactance diagram I am going to rewrite, but this motor, it won't be no longer connected to the system because it is energized and it is disconnected from the system. So now for the calculation of subtransient fault current at breaker A. So at breaker A we need to find out. So for that I am writing the circuit diagram, equivalent circuit once again, the reactance diagram. So here only 3 reactances of the motor will be there, but one will be disconnected due to the energizing of the circuit breaker A. So this is J0.1 and this is as usual the fault point near to the generator side. This is J0.15 and this is all the reactances. So even here also we need to use the Thevenin's formula, VTH divided by ZTH. VTH is always equal to 1. So now we have to find out ZTH here. So how do we find the ZTH means? Again by using the previous calculation only, but here only 3 reactants of motor will be there. So now ZTH will be equal to 3 into 1 divided by J1 plus the series reactance 1 divided by J 0.1, and it is connected in parallel with the one more parallel reactance, that is J 0.15. So now simplify this, we will get the answer for ZTH as minus 4.40 per unit S. So next what we have to do, again we need to use the fault current formula, IF double dash, that is VTH by ZTH. VTH is 1 and ZTH is 4.40. So now substitute this, we are going to get the answer for the fault current as it is 0.227 per unit. So now we have calculated the second case also, but the answer we got in terms of per unit. So now convert this into actual calculation, that is the actual fault current calculation. So the next is the actual fault current calculation. Actual fault current, again use the same formula, IF double dash, actual will be equal to IF double dash per unit multiplied by I base. So I base will remains the same. So now IF double dash is nothing but the previously calculated answer, that is 0.227 multiplied by I base is the same previous calculation, P base divided by root 3 into V base. Of the generator only we have to consider, because here also we are calculating the fault since the fault has occurred on the generator side. So 25 MVA 10 power 6 divided by root 3 into 13.8 into 10 power 3. So after substitution we'll get the final answer as 237.4 ampere. So IF double dash actual for the second case is 237.4 ampere. So next we need to proceed with the third case, that is the momentary current in the breaker B. So we need to find out the momentary current. Momentary current is nothing but the short circuit current or the maximum current present at the breaker B. So now look at the given single line diagram. So for the third case, the circuit breaker need to be energized because a momentary short circuit has occurred. So once the breaker B is energized means it will going to break its contact from the entire power system. So once this breaker B is disconnected means even the generator connected to this also will be disconnected. So now what we have to do, the same reactance diagram we need to rewrite, but here since the circuit breaker B is energized, so this reactance, it is no longer connected to this power system. Okay, so now for the calculation of a momentary current, so I am going to first rewrite the same reactance diagram by neglecting the generator reactance like this way. So now observe here, so this is the reactance of the transformer and this is all the source voltages 1J, and one more reactance is there, 1J only. So this is the fault point, occurrence of the fault point. So before that you must know the formula for the calculation of momentary current. I hope you have remember in the derivation of the selection of circuit breaker. So IMM, the momentary maximum current, will be equal to the subtransient fault current IF double dash multiplied by 1.6. So here 1.6 is by considering the DC offset current also. So now before calculating the momentary current IMM, first we need to find out the subtransient fault current IF double dash. So again you know that IF double dash is nothing but by using the Thevenin's theorem VTH by ZTH. So first we need to find out the ZTH for the above reactance diagram. So here the four reactances are connected in parallel 1J, and it is connected in series with the one more reactance J0.1. So we will get the answer for ZTH as minus 14J. Now substitute this answer in the fault current formula, that is IF double dash is equal to VTH by ZTH. Here also VTH will be equal to 1 minus 14J. So you will get the answer as 0.0714 J. So now next what you have to do, you need to convert this actual calculation. So that is IF double dash need to be converted into actual. So IF double dash actual will be equal to the per unit value 0.0714 multiplied by the previously calculated the base current at as 25 MVA 10 power 6 divided by root 3 into 13.8 kilovolt. So you will get the answer for this is J 74.67 ampere. So now we have calculated with the IF fault current value in terms of actual. So this answer need to be substituted in the momentary current formula. So IMM is equal to IF double dash in terms of actual is J 74.67 and multiplied by 1.6. So you will get the answer as 119.47 ampere. So this is the maximum momentary current when the circuit B is operated. So now remember, the momentary current in the circuit breaker B means the formula for the momentary current from the derivation of selection of circuit breaker is IF double dash into 1.6. So before calculating IMM, you need to first calculate IF double dash here. So IF double dash is nothing but, since the circuit breaker B is operated, so this is going to be disconnected from the system. So by disconnecting the generator connected to circuit breaker B, so this is how we can write the reactance diagram here. So in this reactance diagram, find out Z Thevenin here, and after the calculation of Z Thevenin, substitute that in the fault current formula and convert that into actual. Then this actual answer we can substitute in the momentary current calculation. So that completes the given problem. Thank you.